Okay, so we'll continue the chapter of rigid body equilibrium. So we were talking yesterday about uh, supports. Sometimes we said they might be more than enough, or sometimes the supports are not enough to maintain equilibrium in any condition. So in some cases, some bodies may have more supports than are required for equilibrium, whereas others may not have enough supports, or the supports can be arranged in a manner that would cause the body to collapse. What do we mean by this? So I will explain these two cases. So for example, if you consider the following beam subjected to the action, let's say here you have a roller and here you have a roller. Is this beam can sustain any type of loading while being in equilibrium? Look, you know that roller can only develop reaction perpendicular to contact like this. Okay? So if I put a force, a load in x direction, will my structure be in equilibrium?
No.
No, because I don't have any opposition to this law. Okay? So now, even if I add a third roller, for example, if I put a third one, will it do anything? No, still no. So here, it's true that I have three unknowns, but I don't have possibility of equilibrium. This is called improper. Okay, يعني I arranged my supports in a bad way. If I put the third roller, for example, instead of putting the third roller here, I can just put it here. If I put it in this way, then it will be fine, because in this way I cannot if I apply a load in this way, I can maintain equilibrium. Okay, so when we say improper, this means that the number of unknowns is enough, but the arrangement is not good. And partial constraints is in the case, for example, I have just two reactions while I need to have three reactions. Okay, now what about redundant constraints? Another example, if I put my supports like this, so if I have here a pin and also at the other and a pin also, so how many unknowns I will have? How many reaction unknowns? You know that the pin will develop x and y components. So here I will have two reactions in x and y, and here also I will have two reactions in x and y. So I will have four unknowns, but the equilibrium relation in 3D will just give me three equations. So in this case, my structure will be in equilibrium, but I'm not able to solve for my unknowns. I need a fourth relation that I can't have it from status. I need something else. Okay? So this is redundant constraints, more support than required for equilibrium. Okay? For some structure, and for example, I can have partial constraints, but still have equilibrium, but in certain conditions, not in all conditions. So for example, if I go back to the example of the beam with two rollers, this is partial constraints. It will allow to maintain equilibrium if the load is like this. If I have a downward force on the beam, vertical, then I can have equilibrium by development of reactions like this. But if I have a load in x direction, then it is not possible to maintain equilibrium. So in this case, I will say that depending on the problem, in case I have improper or partial constraints, depending on the type of load, I determine if equilibrium is possible or not. Okay, we will do some problems on this. So here, when a body has redundant support, the problem becomes statically indeterminate. So I cannot calculate the unknowns for unknowns using three equations. As I told you, we need something else, another equation. And in general, it's not given by statics. So for example, if you will take mechanics of materials, you will understand what will be the force equation. But here I cannot, from statics, I cannot solve for the force relation. So I need another type of science to allow me to solve the additional unknowns.
Doctor,
Yes?
can you go back there, please?
Yes. Here or the previous one?
No, here.
Yes.
What if we had AX is opposite to the direction of BX?
Even
And we
with,
have AY
yeah.
and BY are up, and we have the weight with these three forces down. Can't it be in equilibrium?
Okay, look, you mean here, you mean the axis like this?
Yes.
Look, here you have equilibrium. It's not that you don't have equilibrium. But can you find what are the values of the four unknowns? If you have only three equations, can you solve for four unknowns? It's not that you,
Okay.
it's not that you don't have equilibrium. You have equilibrium, but you cannot solve your unknowns. Yani, you say my structure is stable, but I cannot find the reactions as the supports. That's it.
Yes.
Okay.
Aren't مش in the previous slide we were talking about,
Yes,
there is
in the previous slide, it was improper constraints. Look, here they told you redundant constraints. Redundant constraints, this means that you have more support than enough.
Yes, thank you, doctor.
And it's the opposite case, okay? Here you have the case of improper or partial constraints. So in this slide, you have, for example, two rollers. Two rollers can only develop reaction in Y, so no possibility for reaction development in X. Therefore, since you have in your loading X components, then your structure cannot be in equilibrium in this case. Okay? So in case of improper constraints, reaction provided by the supports are not enough to maintain equilibrium. So an example, when all reactions are concurrent at a point, or when all reactions are parallel, then they cannot ensure equilibrium. Let us take examples on this. So given that rod AB is subjected to the 200 Newton force, determine the reactions at the ball and socket joint and the tension in cables BD and BE. So here we have, yes? Okay. So here we have a rod. The rod is first supported by a ball and socket joint at A. If you remember, the ball and socket joint will prevent motion in X, Y, and Z. So it will develop three forces. Okay. While here I have two cables, BE and BD. So they will develop tension forces in the cable. So in this case, I am in a 3D equilibrium problem. I have five reactions, but equilibrium in 3D requires six equation of equilibrium. So here, I cannot be sure if I have equilibrium or not. It is possible to have equilibrium in certain conditions, and in other conditions, I will not have equilibrium. How to verify? I should write the equilibrium equation and make sure that the six equilibrium equations are satisfied. Okay? So let us start together. First, the first step in such problems is to write the expression of your forces. So as we said, the ball and socket joint will develop three reactions, one in X, one in Y, one in Z. So you can write that the force at A is AXI plus AYJ plus AZK. The three AX, AY, and AZ are unknown. Concerning the tension in cable BE, as you can see in the figure, if we call this axis, this is X and this is Y, you can see that TBE is parallel to X axis. This is why TE is TE along I only, while TBD is parallel to Y axis, so it only have a J component. So it's TD equal to TDJ. And don't forget the force applied on the rod, which is a 200 Newton force downward. So F applied is minus 200 K. Now, since they didn't mention anything about the weight, I can consider that it's a massless rod. Okay. Now, the second step after writing the expression of all forces is to apply the equilibrium equation. I will start first by the force relation. You know that sum of forces equal to 0 for equilibrium. So I will write Fa plus tension at E plus tension at D plus F equals to 0. Now I will replace each force by its expression, and I will take I components together, J components together, and K components together. I end up with having along I have AX plus TE, along J I have AY plus TD, and along K I have AZ minus 200. And I know that my result is equal to 0 vector. Now I can do comparison along I, J, and K. So here it's like the method of particle equilibrium. You write the vectorial relation, and then you take three equations, one along I, one along J, one along K. The equation along I will give you that AX plus TE equals to 0. So AX equals to minus TE. The second equation will give you that AY plus TD equal to 0. So AY is equal to minus TD. And the third relation will give you that AZ minus 200 equals to 0. So AZ equals to plus 200. Now, once I am done with this, I can move to second equation, which is moment equilibrium. So for moment equilibrium, I should choose a point on my figure and do sum of moments about this point equals to 0. Now the easiest point to select here is A. Why? Why the easiest one is A?
Because we have three unknowns
Very
at
good.
A, so we cancel them.
Exactly, because since we have three unknowns at A and the three forces are passing by A, so when I do sum of moments about A, I will cancel the moment of these forces. So when I do sum of moment about A, I will only have the moment of the 200 Newton force, which is downward, and the two tension forces. Now you know that in 3D, to calculate the moment of a force, the best way is the vectorial method. Okay, so here for the 200 Newton force, I should do AC vectorial minus 200K. To find AC vector, I need coordinates of points. So I have here, let me check the figure to find coordinates. So here, to find coordinates of point, if you look at your figure, for point C is at the middle of rod AB, okay? So when you have a point, this is not given. You should calculate these. This one and this one, you should find them, okay? Since point C is at the middle of AB, so you know from geometry, from analytical calculation, that x of C is x of A plus x of B over 2, y of C is y of A plus y of B over 2, and z of C is z of A plus z of B over 2. So to find the components of C, I should get the components of A and the components of B. Now, what you can do here, if you want, you can, if I consider that my origin is A, so if A is the origin of my frame, like you can see here in the figure, then the coordinates of A will be 0, 0, 0. And for point B here, okay, you have This is along x, it is 2. Along y also, it is 2. And here 2 and 2. So 2, 2. And here they should add that this is, they should give you this distance. This is 1. So along z, for b, it's minus 1. Okay? So then I have 2, 2 minus 1 for b. And to deduce, since c is middle of AB and coordinates of A are 0, 0, 0, so the coordinates of C will be xb over 2, xc over 2, and gc over 2. So it's 1, 1 minus 0.5. Okay? Now, once I have the coordinates, I can write now the position vectors. So position vector AC is 1i plus 1j minus 0.5k. And concerning the moment of TE and TD, both are passing by B. So I can say that it's AB vectorial TE plus AB vectorial TD. And since AB is common between the two, I can take it into factor and say that it is plus AB vectorial TE plus TD. Okay? Now let us do the expansion of the vectorial product. You can do or the matrix form or the expansion. For example, for the first term, it's easier to do the expansion since here I just have one term. So I start by doing I vectorial k, it is minus j. So I have first minus j, and I have minus, so plus 200j. And this is the first term, plus 200j. Then I do j vectorial k, it's plus I, and I have minus, so minus 200i. K vectorial k is 0, so I am done with this term. For the second term, it's up to you. Or you do the expansion or you do the matrix. Let us remember how to do the matrix. So I take the first line as ijk. So here, if you want equilibrium, it's just, and if you know well the chapter of moments, equilibrium is very simple. Just you do sum of forces equals 0, sum of moment equals 0. Just what is new is the supports. You should know the type of supports in 3D, and that's it. So here the first line is 2i plus 2j. The second line is 2i plus 2j minus k. So 2, 2 minus 1. And for the third one, it's TE and TD and 0. Okay, so if I do this, I have here plus, minus, plus. So this vectorial expansion will give me along I first. Okay, it's 2 times 0 minus minus TD, so plus 2 TD. So along I have 2 TD. Now along J, 2 times 0 plus TE, and I have minus, so minus 2 TE along, minus TE, sorry, along J. And along K, I have 2 TD minus 2 TE, so plus 2 TD minus 2 TE along K. Okay, and now combining with the first vectorial product, which gave me minus 200i and plus 200j, I can take I components together, j components together, and k components together. And now I will obtain by comparison along I, j, k 3 equations. The first one is that TD minus 200 equal to 0. So this will give me that TD equals to 200. The second equation will give me that TE is equal to 200. And as you will see here, the third relation is just a verification one, because here you have 6 equations, 5 unknowns. So the sixth relation will not give you any additional information. It will just tell you if equilibrium is possible or not. So here, since you have already found in the fourth relation that TD equal to 200, and in the fifth relation that TE equals to 200, Then from these results, you know that TE should be equal to TD. And the sixth equation, it's a verification of this, because the sixth equation will just give you that TD is equal to TE. Okay? So you say then it is verified and equilibrium is possible. If the sixth equation, for example, gave you TD equal to 2TE, this will be in contradiction with the previous results. Then you say the equilibrium is impossible. Okay? So this is a case of partial constraints. So I don't have six reactions, but I have, it is possible for this type of loading to have equilibrium. If I have another type of loading, the sixth equation might not be verified, and then I can say for the type of loading given, for example, equilibrium is not possible. Here, for this type of loading, just a vertical reaction, equilibrium is possible. Okay? So here, once I get from these three relations, I get AX, TE, and TD. Sorry, from these three relations, I get TE and TD. Then I replace back into the three equations of sum of forces equals 0. I can get then what is AX and what is AY. Because already AZ is 200. Since AX is minus TE and AY is minus TD, so AX equal AY equals minus 200, while AZ equal TE equal TD equals to 200. Any question on this problem?
Doctor, can you please repeat why it's RB times TE plus TD?
Just can you repeat the question, please?
In the second line,
Yeah.
can you please repeat why it's TE plus TD?
Okay. Because here, if you are doing sum of moments about A, you have first the moment of the 200 Newton force, which is RC vector vectorial 200 minus 200K. To find the moment of TE, what should you do? You take the position vector AB and you do AB vectorial TE. So you have AB vectorial TE. This is the moment of TE plus the moment of TD. Also for TD, the position vector is AB. Okay, so plus AB vectorial TD. Okay. Now, from the vectorial product calculation, when you have a vector in common, you can take it into factor. So you take AB vectorial. What do you have in common? TE and TD. So it's AB vectorial TE plus TD.
So, okay, thank you, doctor.
Welcome. Any other question on this? Okay. So this is the chapter of rigid body equilibrium. We are done with the chapter. I will start with you. I will open a new session to start review problems together on this chapter. Okay? And concerning exam 2, we will discuss together on the group the date. I think it will be just after Easter, so maybe April 10, maybe, will be good. Okay? So we will talk about it on the group. Now let me open a new session.